Okay, today we're going to talk about slope fields. Okay, slope fields are basically where we take the derivative of a differential equation, dy dx, and we evaluate the derivative at all the points on a particular interval or the particular xy plane that we are given. By evaluating the derivative at each of the points, what we can do is we can see, for example, at these points, what the derivative is doing at particular values. So we know what the slopes are at individual points. Using the idea of linear approximation that we did earlier in the unit, that if we have the tangent line at any one of the points, that the new y value is moving from the original y value, the point that we do know. Okay, so if this is my first x1 and y1, a point that we do know, but we're given an initial value. If I know the slope at that point, then I can draw a small tangent line and use that tangent line to approximate the next point. So without actually knowing the next point. So the new point minus the old point can be approximated by doing the difference between the x's. The order absolutely does matter. Okay, so it's the new x minus the old x, the new y minus the old y. If we add over the old y, that the new y is equal to the derivative times the difference in x's. So we've done this as a linear approximation before. We estimated new y values using the tangent line instead of the actual function value. Okay, so on here, if then I know the derivative, I could move over a certain distance and then I reevaluate the derivative again. So by reevaluating the derivative at the new approximated point, I can then estimate a tangent line there that would move me over far enough to get an approximation for the next line. So by moving around the tangent lines, I can approximate the actual curve. Obviously, the smaller the difference in x is, the smaller amount that I move over, the more accurate this will be. Okay, so what that gives me is it gives me an approximation for a specific curve through a point. What slope fields very often give us, however, is they give us what it would look like if we did not know an initial value. So remember when we antiderive something, such as x squared, we actually get a function plus c. Okay, so that plus c, without an initial condition, we really don't know exactly which of these curves we would pass through. So it's the idea that we could get any one of the 1/3 x cubes shifted up or down. So I don't really know which curve I have, and the slope fields give me actually the entire group of possibilities for that curve. So if I were going to fill in here into the derivative of y with respect to x equals y, if this were my derivative, then the only thing that really matters as we go across is the y value. So if y is -3, then the slope is going to be -3. If y is -2, the slope is -2, -1, 0, 1, 2, and 3. If I move over to the next point, if y is -2 and the x is -2, really doesn't matter about the x. What only matters is the y value. So as long as the y is -3, then the slope is going to be -3. If the y value is -2, then the slope is -2. If the y value is -1, then all the way across the slope is -1, 0, 1, 2, and 3. So that means if I were to graph this, I tend to approximate, so before you write this down, if I were trying to do a -1 slope or 1 slope, if I were trying to do a -3 slope, I would kind of guess from here exactly how those were going to fall. So on there, at -3, I need to have a -3 slope, which according to this would be about that angle. So all the way across, the slopes would be -3. And then they would be -2, and then -1, and then 0, and then 1, all the way across, 2. So what they're looking for on the AP exam, to get a little higher for 3, is they're looking specifically for the points to have the horizontal and the vertical in the right places. And then they're looking for positive and negative and steepness. So these problems are typically worth 2 points. Your first point is going to come from getting the positive and negative correct. The second point has to have both the horizontal and the vertical correct is the first point. The second point is going to come from having positives where you should, negatives where you should, and that they get steeper. So you don't have to have these perfectly as 1 and -1, but if you have these as your estimate for 1, then the ones above that have to be steeper to represent the 2 and the 3. So steepness and comparison, really not perfect ones. These are just sketches. So on here, what this is telling me basically, without any more information, I don't actually know what curve we have. But were I to give you the information that we started passing through the point 1, 1, were we to pass through the point 1, 1, meaning I started here, that I could know exactly which curve we're on. So I'm going to start with my slope field. It has to be exactly that slope. As I move over, it is not that you're going to drive like a crazy person through all these things. That is not our goal. Our goal is to not be in disagreement. So basically, we're all a bunch of politicians, and we agree with whomever we're closest to. So if whomever we're closest to wants to raise taxes, then we'll agree with them and say, yes, that's a great idea. I like your program. We'll raise taxes. If someone we're next to says, no, 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 we're going to lower taxes, then that would be what we would do. So we just agree with whoever's close to us, so it makes us look good. So I'm going to move over, and as I get closer to this line, or as I cross over the line here, I have to change and match that slope. So the important thing is that you never disagree with anyone on your row or column. So as I move up, as I get there, I can't come over and then go up. I would have a slope right here that disagrees with pretty much everyone he's around. So what I want to do is, as I move up, make sure I transition so that by the time I get there, I'm matching that slope without having any sharp turns or jerks. And then as I move down, I need to transition so that I am matching the fact that we have a horizontal asymptote and 0 slope there. Okay, now, I might decide that I have a different opinion and that I would like to agree with someone else if I have a different starting point. So maybe this time I'm going to have -2, 0 as my starting point. So if -2, 0 is my starting point, I'm not allowed to disagree with this 0 slope here. So really I'm right on top of the horizontal axis. I can't do anything there. I can't do anything at all for that asymptote. It would be straight across. Whereas if I were to have started, let's say, at 1, -1, then I would have a completely different opinion, and I would have to match here. So we have lots of different possible answers to this derivative, depending upon what our plus c turned out to be. Okay, so for the next one, 1 over x is the derivative, so hopefully we know by now that if we anti-derive 1 over x, we would get natural log absolute value of x plus c. So a couple of things are affecting us. The plus c is a shift up or down. The absolute value is also doing something to our graph. So now if I put -3 in for the y value, it has no impact this time. The only thing that matters is the x. So as long as x is -3, my slope is going to be -1/3. As long as x is -2, my slope is going to be -1/2. As long as x is -1, my slope is -1. Notice what happens, however, if x is 0. When I divide by 0, I get an undefined slope. So for this whole time, my slope is undefined. As long as x is 1, my slope is 1. If x is 2, my slope is a half the whole time. If x is 3, my slope is going to be a third the entire time. So if I have an undefined slope, that really means if x is 0, I have a vertical asymptote. And again, we have a -1 slope the entire time that x is -1. We have a -1/2 slope. So I'm really just going to have a negative slope still, but a little flatter. And then a -1/3 slope has to even get flatter after that. We have a +1 slope when x is 1, +1/2 slope, and a +1/3 slope. So notice that this does in fact look like the graph of natural log absolute value of x shifted up or down. So if 1, 1 was my initial point, I'll again have to make sure that by the time I reach a certain area, that my slopes don't disagree. So I'm trying to agree with whomever I'm closest to. But now because of the absolute value, I would technically have an answer on the other side as well, because it's x absolute value, not y absolute value. If I were to have the point -2, -1, starting here, I would have a different shift. And so I would have the other side of that graph as well. So again, what I don't want to do is disagree with a slope that I'm close to. So again, it's not about hitting all of the dots. It's not about missing all of the dots. It's about matching the slopes that you're close to. Okay, one thing I want you to notice about these two is notice what happened when I had a y-only derivative. If the derivative was y-only, the x values never mattered. So going left and right had no impact, only going up and down. Similarly, if I had no y in my derivative, if x is the only thing there, then x is the only thing that matters. Going up and down made no change, but going left and right did. That'll matter when we start doing matching questions. Okay, so for this one, the easiest thing to do is start with how the AP would grade you. I'm going to start with letting x equal 0 and y equals 0 for this graph. So if x is 0, then the derivative is going to be 0 the entire time. If y is 0, however, we're going to have undefined the whole way across. So if the x is 0, we have 0 slope. If the y is 0, we have vertical slopes. And notice who wins. Vertical is going to win over horizontal every time. If we have 0 over 0, okay, that is not going to be something that we can assume is 0. Okay, we don't want to do that. So it turns out being vertical. Okay, now notice what happens. If x is 1 and the y value is -3, I'll actually have +1/3. If x is 2 and the y value is -3, I'll have +2/3. If I have 3 and -3, because of the negative that's here, I'll have negative over negative, which makes +1. If the x is negative, then the numerator becomes positive, and then we have -1/3, -2/3, and -1. If the x is if the x is -3 and the y is -2, we have 3 over -2, 2 over -2, so -1, 1 over -2, so -1/2, -1 over -2, +1/2, -2 over -2, +1, -3 over -2, 3/2. So notice what's happening to the left and right. Each of these are matching. It folds out and reflects, but with a different sign. So I can really do this right-hand side and then reflect across. So -1, -1 is 1. -2 over -1 is 2. -3 over -1 is 3. So I can reflect -1, -2, -3. So then we have -1, -2, -3 reflects as 1, 2, 3. -1/2, -1, -3/2 makes 1/2, 1, 3/2. -1/3, -2/3, -1 makes 1/3, 2/3, 1. Now what I think is easiest on this is to check the diagonals here. I have a slope of 1 and a slope of -1 along those diagonals. So I can do slope of -1, -1, -1 along this entire diagonal, slope of 1 along this entire diagonal, and then working across from there, notice what happens as I go up. I have in the first quadrant, I have negative slopes that are getting flatter. And steeper depending upon which direction we're moving. So here I get -1, -2, -3. So you can kind of tell what starts to happen there. Slope of a half, slope of a third, 2/3, 1 and 2, 1, 1.5, 3. So notice what's happening. We're making kind of a circular shape. And this is in fact the derivative of a circle, implicitly. Now what I like to do for one like this is look where I would have my derivatives to be 0. If I wanted my derivative to be 0, it really means that -x would have to equal y, or y equals -x. So I'd have a 0 slope along y equals -x. Okay, what happens above or below that? So if I were to use the point on here, so I said we had a 0 slope along the diagonal. If x is 0, then we're going to have 0 plus y. So this is going to be 3, 2, 1, -1, -2, -3. So I'd have a slope of 1, a slope of 2, a slope of 3, -1, -2, -3. If x is 1, then our slopes from the bottom up are -2, -1, 0, 1, 2, 3, and 4. So we have a -2 slope, a -1 slope, 0 slope, 1, 2, 3, and notice how I'm just getting steeper. So notice what happens then along the diagonal. If I use x is -1, y is 0, I get -1. If I use x as -2, y is 1, I have a slope of -1. So notice what's happening along the diagonals this time. I have a -1 slope along that diagonal. If I use x is -1, y is -1, I get -2. And notice what's happening along this diagonal. So patterns can help you out a lot in doing these. So I have a slope of -2. And then I'm going to have a slope of -3. And then -4. And then -5 and -6. Which are almost pretty much straight up lines as far as we can tell by the eye. And similarly, I'm going to have a slope of 1 along the diagonal above the 0. and then 2, and then 3, and then 4, 5, 6. So notice that we have a slant asymptote for this one. Now the solution is any circle for this question centered at the origin. So if we have the circle that goes through 1, 1, that does not mean we have a radius of 1. It actually means our radius would be root 2. So all of our diagonals would be at 1. But vertically and horizontally it would not. Like so. If we went through negative 2, 0, that, however, means our radius is actually 2. So that does not mean we're going through diagonally at 2. Okay, now for this next problem that we just did at 1, 1, remember what I said about passing through whoever you're close by? So as we go across, by the time we get to x is 0, we have to have a 0 slope. So we're slowly adjusting as we move so that we never disagree with whomever we're closest to. So we're going through negative 2, negative 1. We would have a very drastically different piece of graph. But they would both have to approach the asymptote. Okay, so remember what I said a little bit earlier about matching. The easiest thing to do is to look for whether you have just x, just y, or a blend, and then look for the zeros. So this one tells me that we have just x, so left and right matters, and up and down doesn't really matter. Also, we only have a 0 slope if x equals 0. The slope is going to be 0. Okay, so that means x equal to 0 should be our only 0 slopes. So notice on these we have diagonal slopes of 0. Here our slope is 0, but not when x is 0, it's when y is 0. So that can only be number 6. So number 6 has to be A. Similarly, if x is positive, the slope is going to be positive. If x is negative, the slope is going to be negative. Okay, so the easiest one to do next would be to know number or letter C. So the y value is going to give us our only 0. And if y is positive, the slope is positive. If y is negative, the slope is negative. So that would be this situation, number 8. 0 slope when y is 0, positive slope when y is positive, negative slope when y is negative. So we've done those two. Okay, now for B and D, it's a little more complicated because we're changing based on both of these, but you still want to look at your zeros or undefined. So I'm going to have a 0 slope if 3x plus 2y equals 0, meaning negative 3x equals 2y, or when y equals negative 3 halves x. So that's along this negative line. So this would have to be D. Similarly, I would have a 0 slope for letter D if x cubed minus y cubed was 0, meaning x cubed equals y cubed, or when x equals y, because taking an odd root is not plus or minus. So that's only going to happen here. The higher the powers we have on these, the little more complicated the spin is going to be in the middle, but that still has to follow the pattern. So for D. Okay, matching again. So the derivative for this is 1/2 x plus y, so it's only where x is mattering. And one thing I want to point out before we do these as well. Notice what I said about this one. The derivative of this was for a circle, but then going back over here is something a little easier to see. If the derivative is 1 over x, I know the antiderivative of 1 over x is natural log of x plus c, then this has to be a natural log graph. If I know the antiderivative of 2x is x squared plus c, then this has to be a parabola. These slope fields will always match the y. They don't match the derivative themselves. The derivatives give us the constant numbers to graph, or the slopes, but they don't give us the function. So if I'm looking at this, the derivative is 1/2 x plus 1. That'll equal 0 if 1/2 x equals -1 or x equals -2. So I have 0 slope if x equals -2. Okay, that's going to happen at B. But also, if I anti-derive 1/2 x plus 1, I would get 1/4 x squared plus x plus c. This is a parabola. B is the only parabolic shape that we have in our choices. So use everything that you need to help you match these up. Okay, for 10, the only time I'm going to have a 0 slope is if y equals 0. If y is greater than 0, then the slope is going to be positive. If y is less than 0, then the slope is going to be negative. That matches with D. Huh, that's funny. I wrote B as the answer for B. Number 9, this is going to be number 10. Okay, for number 11, I will have a 0 slope if and only if x equals y or y equals x. So that's going to happen only for letter C. So number 11 is letter C. And lastly, for number 12, I'm going to have a 0 slope if x equals 0. I'll have an undefined slope or a vertical line if y equals 0. So that only happens, and it's harder to see on the slope fields as the circle comes around, that I would have the vertical slopes here. So that is going to be 12. Okay. Now, use my calculator to draw a slope field for the differential equation dy dx equals xy. Notice that the slope would be 0 if x equals 0 or y equals 0. So I actually have 0 slopes, so they're kind of hard to see because they're right on top of the axis. Okay, so sketching the solution through the point 0, 1 is already shown. If I were to sketch a solution through 0, 2, that would mean that we would have to have this shape. Now, on these, what's really important to notice, this is a hyperbolic type shape. However, you have to have a function, and a function has to pass the vertical line test. You should never draw something that's not going to pass the vertical line test. Okay, so we have another calculator drawn slope field, so I want to point out that our slope is going to be 0 if and only if y equals -x. So if we want to sketch the solution through the point 0, 1, 0, 1 would be here. So our solution would trace up. It does not hit or miss the lines. We don't care if it hits them. We don't care if it misses them. We just want to make sure that if I compare, nowhere in between here am I drastically different from that slope. So I definitely don't want to be like tracing around to miss them or hit them, because you don't want to have a situation where your slope doesn't match their slope. So just trace slowly and constantly adjust your slope as you move across so that you're matching the slopes around you. So if we're going to go through -3, 0, that would be here. So notice it's not right on top of a line. So as I go up, I'll adjust, and I'll continually adjust one stroke at a time, not again trying to necessarily draw without picking up my pencil. but just trying to make a smooth curve that sort of matches the slopes around me. So that's the end of the slope fields lesson. And we'll look at the first part of your worksheet, that's the homework, but we won't finish that one together. You have to finish it for homework.